behind you.
And the last talk of the session is given by Sridhar, and it's about relaxed modular PCS from arbitrary PCS and application to SNARKs for integers.
All right. Yep, thanks for the intro. I will be talking about something very similar to the last talk. And we're going to focus mostly on integers, not the other things that we've seen. Also, a disclaimer, Zinc Plus came out very recently and hasn't been included in the slides. So assume that related work consists of Zinc Plus as well. The prior work is there, though. All right, so this is, the title has been shrunk, so it fits on the slides. This joint work with Ali Reza, Dimitris, and Babis, and this was done when both Ali and I were at Lagrange. All right, so I'm going to skip this slide. You have prover, verifiers, prover knows a witness, and you send a proof. And you have the standard properties, completeness, knowledge soundness, and succinctness. I'll, of course, specialize these a little more later as I go into describing what exactly we need. But for now, these standard things, we've seen all of them at least 5 times. You might have seen the exact slide maybe 3 more times as well. All right, so again, this legwork has sort of already been done by the last talk. I don't need to motivate all of these that much. But yeah, so we would like to, we have SNARKs over finite fields. And unfortunately, the things we want to prove are not over finite fields. And we have here, your favorite SNARK. And on the other side, well, my favorite computations, maybe not yours. And ideally, we would like our favorite SNARK to be there, but we have this gap. And well, usually we bridge this by emulation. Say, OK, let's embed our non-native arithmetic into your field. And you have blow-ups, you have different issues. You have performance issues, or you have soundness issues, because they're hard to do, right? So the goal is let's try designing SNARKs that are native and not non-native. So one thing it turns out is for most of these applications, SNARKs or bounded integers sort of suffices. Any sort of field that you work with or any ring you work with can be emulated over integers using basically one constraint, right? And as an example, let's say RSA decryption. This is taken from Campanelli et al. Slides. That was one of the prior work that I'll talk about in a bit. So yeah, so suppose you're decrypting. Reducing any modular equation over fields is very simple, or over integers. All you have to do is say, OK, I know a k such that m plus k times n is equal to my left-hand side. And that proves that my value is actually correct modulo n. Of course, you need a range proof as well, but those are also simple over integers. And these are numbers. I'm sure these numbers have improved, and it's not 90,000 anymore. But yeah, this is one of the initial numbers that we had. And this sort of suggests that we do need these tools. So we have the standard blueprint of, OK, PIOP plus PCS gives you SNARKs. And similarly, CH24 tells us that you can do something very similar for SNARKs or integers. You just give me a modular PIOP and a modular PCS. What are these things? So mod PIOP is essentially the same thing. Instead of sending polynomials, you send integer polynomials. And verifier does the same interaction stuff. And your queries are now going to be modulo a random prime q. And then the verifier makes a decision. And these things, it turns out, are actually sort of almost reusable from prior work. We don't need to construct new things. And the main sort of contributions I'll talk about are in the mod PC part. So this, for now, looks kind of similar to what we've seen before. I'm just going to define it. So you commit to an integer polynomial, and you want to prove evaluations modulo some prime q. And the setup is now going to care about 2 things, not just the degree, as usual, but you also care about the bit length of your integer witness. Maybe your coefficients are really large, so your setup will sort of depend on that. And you have a committer key, a verifier key, and then you have the same thing as usual. You have prover verifiers, the prover commits, the verifier sends an opening point, and then the prover is going to evaluate, produce a proof, and the verifier can check it, right? And completeness and extractability are standard. It's just that now you need to extract an integer polynomial, not just a polynomial over a field. So why is this not just a regular PCS? The only main difference here is that this queue is not known at commitment time. So, and not specifically not at setup time either. So most of your standard tools over finite fields are not going to work here because you usually need to fix the field, right? So all of your constructions that even maybe or field agnostic do not satisfy this definition because even though you can choose any field, you might need to know them at setup time. You cannot sort of choose them on the fly. So we have these two. Well, add one now for Zinc Plus. I've not added it there. But we have these different asymptotics. And know that, as before I mentioned, n and b, n is the degree of the polynomial, and b is the bit length of, or the maximum bit length of any of your coefficients, let's say, right? And both of these have their own ups and downs. GO stands for groups of unknown order. These are not very fast in practice, not post-quantum secure. So ideally, we would like to make everything green, right? That's the goal. And the other downside here is also we want the verifier and proofs has to be succinct in both B and N. This is not the case for regular PCSs. We don't care about the bit length because everything's a field element. The field element's lambda bits, so it's fine. But here, the bit length can be arbitrarily large. If you're looking at, let's say, RSA stuff, it might be 2,000 bits, 3,000 bits, and so on. And so you'd like the verifier and proof size to be sort of independent of, or not independent, but logarithmic in that. So the goal is, can you build a mod PC that achieves this sort of full succinctness? And full succinctness, I mean in both N and B, right? That's sort of the goal of these mod PCs. And we sort of dive into this a lot more. And what we show is we build this thing called Karen, which is basically a transformation that says, OK, give me any PCS, your favorite PCS. I don't care which one it is. And I'm going to build a mod PC from it. And of course, the asymptotics at the end will depend on what your initial PCS was. But we just give one example here. So, oops. Yeah, so I'm just adding a row here. Everything's green, as we would expect. I guess all of these are also transparent proof systems, so none of these require trusted setup. We instantiate this a tensor switch, which you might have been to a talk before about that. And one nice thing is even though the first row has, well, basically everything's green, there's still a difference about the asymptotics because you have n times b here, and we still sort of remove the multiplicative factor. So we're sort of, yeah. OK, I should specify these are. OK, I'll come back to you later at the end. The verify time ends up being just log BNN. And the random oracles because of the PCS we choose. And some additional contributions that sort of are required to build these things. We need all the integer operations. We've seen some of them in the previous talk as well. How do you prove integer addition, multiplication, etc.? And these will be over similar bit vectors as well, as we've seen before. So one sort of, I guess, higher level picture I want to talk about before we start going to the techniques is what is sort of the main paradigm to get this sort of full succinctness notion. So we have two sort of variables here. One is we need to get succinctness in the degree of the polynomial. The other thing is in the bit length, right? And so the first step in a lot of these integer protocols goes as follows. You start with proving, let's say, a polynomial evaluation over a large number of small witnesses. By small, I just mean field elements, right? And, well, I'm going to say, OK, I'm going to have a first step that's going to take this entire thing and give you something that just reduces to proving a small number of equations or a small number of variables. And these are going to be really large variables. And this is possible over integers because I can sort of take 10 integers and not compress, but encode them into a really large integer. And this works fine. This cannot be done information theoretically for, let's say, finite fields because you'll run out of space. You cannot compress, let's say, 10 field elements into one field element. That just doesn't work. And the second part is going from large integer witnesses to the verifier only looking at small integer residues. And so this is sort of a common TCS technique of fingerprinting, and we show how to use this in our setting. So OK, let's see how we do sort of the first part. So the first starting point is we need to commit to integer polynomials. So how do we go about that? Well, we sort of look at the KCG commitment scheme. What do you do there? You commit to a polynomial by evaluating it at a point. It's a hidden point here, of course. And we do something very similar. We say, OK, the point is not hidden. We want to have no trusted setup. We want to be transparent. And let's just do the same thing. Compute P of alpha and commit to P of alpha. Of course, I haven't told you how to commit to an integer. But all I've done is reduce committing to a polynomial to committing to an integer. This alpha has to be large, so you can actually reversibly get P from P of alpha. But this just says that, sort of tells you that if you want to commit to, or if you want to work with lots of numbers, you can sort of reduce it to working with just one number, but really, really large, right? So how do you commit to an integer? Well, one option is, well, groups of unknown order. These groups are basically groups where the order cannot be computationally, I guess, a computationally bounded adversary cannot compute the order of the group in a reasonable amount of time. So here, well, the commitment is just going to be g to the power z. And this is binding to integers. And this is fine. The only downside is that they're not post-quantum secure, and they're also pretty slow in practice. But the good thing is this makes operations very easy, because you're committing to the integer directly. All you have to do is, to add them, you just homomorphically add them together. You're fine. The other option, which is more generalizable in some sense, is you commit to the bit decomposition of your integer. And this one is, you can choose whatever vector commitment you want. You can make it as fast as you want it to be. But unfortunately, you're going to have problems, or not problems, but at least it's going to be harder to prove things like addition and multiplication, simply because you have to worry about carries, you have to worry about what multiplication algorithm you pick, and so on, right? So our approach, we picked the second one just because of the generalizability. We want to work with arbitrary PCSs. So we use the MLEs to commit to them. So you can use your favorite multilinear polynomial commitment scheme. And this can be faster and post-quantum secure. And we also sort of remove the second con by saying, OK, we'd actually design these arguments for you. And for now, assume that you have these tools. I'll describe what these tools, how they work slightly a little bit later. And now given these, how do you evaluate this committed polynomial at some point? So let's say you have this polynomial. You have this number e sub p, which is just the evaluation of this polynomial. And you commit to this. And you want to convince the verifier that p of y is actually z mod q somewhere. So let's say the verifier computes this other number e sub y. Verifier does not actually do this. It's going to be too expensive. But the verifier is, let's assume the verifier does it. This is basically y of alpha, where y is the evaluation point. It just reversed, right? And you might possibly see where this is going. Let's multiply ep and ey. And you basically get something that looks like an integer polynomial multiplication. And if you look at the coefficient of the term alpha to the n minus 1, you exactly get p of y mod alpha. And you have some terms on the left and the terms on the right. I've denoted them by L and R, which are just junk. You don't care about those things. Those are just sort of shifted inner products, right? And so what does this sort of do? It's saying that, OK, the prover is committing to 4 integers, L, M, R, and H, and proving that as long as this equation holds and this equation holds, and some other range proofs hold, I'm sort of skipping over some details, we're sort of good to go, right? So this sort of does the first part of the paradigm. It's saying, OK, I have large number of smaller witnesses, and I'm going to reduce that to a small number of large witnesses. Yeah?
Why using bits rather than
You
larger
can. There is no necessity to use bits. But you still sort of end up with the same sort of issues with addition, because you still have to worry about carries, you still have to worry about, but it's just sort of a constant savings in some sense. Asymptotically, you still end up with the same issues. It's a public thing. You can the only value, the only constraint that satisfy it is that it has to be really large. That's it. And the largeness depends on the something in the setup, which is what's the maximum degree you want to support, what's the maximum bit length you want to support, and that tells you what alpha should be.
The PCS works for every y or just random y?
We only need it at random y to construct most SNARKs, but you can also support arbitrary y. But you have to repeat it twice, basically. Because we sort of piggyback on the randomness of y to prove some properties, but once you prove those properties, you can use arbitrary y's.
I was just thinking if alpha is known, maybe that means there's some y you can cheat at that is rare.
No, that's not the case. All right, so we've sort of shown with this that the first part, sorry, that's going forward, not back, is we reduce computing or reduce proving something over a large number of witnesses to a small number of witnesses. It's just they're really large now. So how do you do the second part? So this uses sort of the fingerprinting notion, where we also seen a prelude of this in the previous talk, is we call this mass stack. And so let's say we have this integer polynomial with t coefficients of beta bits each, and you want to prove that this polynomial evaluates to 0 over the integers. Of course, this looks like exactly the problem we started with. Why is this going to be any easier? The only difference is now all we care about is for it to be magnitude succinct. We just care about the verifier and proof size being succinct in beta, not in T. Because we've reduced T already, so all that matters is for a verifier to be, if the verifier is linear in beta, I'm happy. The prover is going to be 2 to the power beta, of course, but the verifier just has to be beta. And this requires a lot of sort of sub-protocols to build. These are similar to what you've seen in the previous talk as well. Specifically for multiplication, we need to actually use some entity-style multiplication, because otherwise you would be sort of quadratic in the bit length, which is not ideal. Right? So we've sort of gone from one step to the next step as well. And this protocol basically relies on the fact that, OK, if I want to prove an integer equation over the integers, it just suffices to prove it modulo a random prime. And that's all that matters. And so the verifier sends a random prime. The prover is going to give you residues modulo that prime, and you can check the equation using those residues. So what have we done? We've sort of reduced this to, let's say, just the prover committing to like 5 things and proving some things on these 5 things, like additions, multiplications, and range proofs. And we've sort of told you how to do these things in a toolbox. Right? But unfortunately, what do we have right now? We've shown that P of y is z mod alpha. And the coefficient, this is a technical thing that I sort of won't cover. You can talk to me later about it. We show that coefficients of P are bounded rational. So small numerators, small denominators, not integers, which is what we wanted. Yeah, so what we want is actually for P of y to be z mod q, and the coefficients of P to be integers. We can go from bounded rationals to integers using lookup tables or some kind of lookups. This from the Zinc paper, prior work of both the last talks. And so we sort of focus on the first part. The second part, I can talk to you about it later. There are still sort of open questions there. And so now the question is, how do I go from z mod alpha to z mod q? One thing you might notice is if alpha was, let's say, already 0 mod q, this would be very simple. Just take the equation mod q. But the problem is you don't know what q was when you're choosing alpha. So you can't actually do this. So how do we do this? We sort of do some kind of modular switching. You may have seen this in many different contexts, but this is, I guess, well, morally the same thing, but different techniques. So, well, what does the protocol sort of structure look like? We pick an alpha. Prover commits to something. There's a random modulus, and they evaluate to get this guarantee, right? So then you proceed the sort of a very similar thing. Let's say take another beta is equal to alpha times q, commit to it, evaluate to it. And crucially, you use the same z again. Or you basically force the prover to evaluate to the correct z. And you can actually show that this implies that you can basically show that p alpha of y and p beta of y are the same mod alpha. And using Schwarz-Zippel, because y is random, this is where we use the randomness of y. But basically, the polynomials must be equal. And we sort of now switched our polynomial from base alpha to base beta. And going from P of y being correct mod beta is very simple. It's very simple to go from that to being correct mod q. All you have to do is take the whole equation mod q, and you're done, right? So a quick recap, sort of round it out. So you commit to bounded integer polynomials given any PCS using a bit commitment style commitment. You design a protocol to show the correctness modulo some large alpha. And of course, doesn't suffice. So then you switch to modulus beta with a random value of q, a random factor of q. And then fingerprinting with this gives you sort of correctness over the integers, which is what you wanted at the very beginning. Fingerprinting, I'm just saying, is because q itself was random, that's what shows that the value must be correct over the integers, because q was chosen after the commitment was made. So some sort of open questions I want to spend a tiny bit of time on. Let's see. OK. So, well, this sort of relaxation, it's also in the title. Why does this exist? So it turns out that the rationals is unlike, let's say, Zinc plus, where the rationals were a feature. Here it's sort of an anti-feature, because what we can extract is rationals. But it turns out that if the rational denominators are small, the prover success probability is also, let's say, as high as small the, OK, let me phrase that better. If, let's say, your denominator is, let's say, 1 by 2, also the denominator is 2, then the prover success probability is basically half. So it's very unlikely that you would catch the prover cheating. Well, you will if you repeat it a bunch of times, but it's going to be hard to catch a prover cheating if the prover is using small denominators. So it's sort of very hard to get rid of this. And essentially what it boils down to is how do you sort of amplify rationalness given a vector of rationals? How how to do this, I may need to ask some coding theorists, but that's a different question. So the other thing, unlike the last talk, this is not yet practical. We're still not concretely as efficient. We did some proof of concept tests, not great. I'll stop there. I'm not going to explain more about how not great it is. Yeah, and the other thing is, well, we also had this question in the last talk. Like bit commitments are not great because you basically add an overhead of the bit length of your number. And are there other ways to sort of commit to integers? The group of unordered-based commitments are actually kind of nice in this setting because, well, a commitment is just one group element, and all you have is one number in the exponent. But if you need to commit to, let's say, a bits, you sort of grow, your prover time sort of grows with the bit length. It would be nice if you have other representations that work. Something like a CRT representation could potentially be smaller in a sense. But it's hard to make that work as yet. So those are some questions. Hopefully, we'll have some answers. But yeah, thanks. I'll stop there.
Questions?
So if the integers and if intermediate values go over the bound, what happens? Is there a soundness problem then?
No. So because you're doing range checks also throughout the process, you're most likely going to be fine. Not most likely, you're going to be fine. I shouldn't say most likely.
But in that case, if you had used a SNARK over a prime that is larger than the bound and just done the same range checks, then you would have achieved the same result.
Yes,
right?
but the problem is we might need to work with bit lengths that are much larger, and they won't even fit in your field. Not just, say, 32 or 64-bit numbers, but let's say 2,000-bit numbers.
Oh, I see.
So if you do a sort of a limb decomposition, let's say, and break them into large enough numbers to fit into fields, you still need to have some space so you can actually do operations over the fields and then reduce them again. But yeah, that works.
Okay.
But potentially that emulation might be more expensive than, yeah. But again, concrete efficiency is still a question here. So
exactly. We
yeah.
don't know it's actually more efficient
I don't know the answer.
than doing
Yeah.
CRT representation over a
But the CRT, I think we need to be careful just because the guarantees you get at the end might be modulo the product of the primes and not modulo the integers, which is going to cause soundness issues.
I see.
A question.
Yeah, can we go back to the prover time thing? Yeah.
Yeah, I think I made a mistake.
Okay, but can we go back to it so we figure out the...
Yeah.
So the question was, I'm going to repeat the question. At some point there was a...
Yeah, the question is the n times b should be there.
Yeah. It was sublinear in the width.
Yeah. I might have to come back to you after the talk because I also don't remember exactly what. Yeah. This might, okay, here we are. I might have to come back to you later.
Yes, also, okay, sorry, just checking. Yeah, ours looks good. Yeah, that was just at this point, that was...
Yeah.
Another question I had very quickly was, what's the difference between a mass-duck and a fully succinct argument over the integers?
It's not succinct in the number of witness elements.
Okay.
Because basically what the prover is going to be doing is sending you all the residues for all its witness elements.
Okay, so, all right. So if you have, say, like the RSA constraint system, you have 16, your witness size is 16. And by the way, I think it's 16 constraints, not 12 as in your slides.
Okay, sorry.
Unless you can do 12. So you're saying, look, I don't care about this number 16 because it's going to be, is that the...
what do you mean by I don't?
So normal magnitude succinctness, but not witness succinctness.
Oh, yeah,
right.
Right. I don't care about the number 16. I only care about reducing the bit length to something.
Yeah, the 2000.
Yeah. The first step is sort of getting rid of the, I guess, the degree or the arity of the circuit.
Thanks.
Are there other questions? Yeah.
Let's say you have a statement where you want to do some things over large integers and other things over a specific finite field. Say that it's an elliptic curve computation and that's a natural field. Is there a way to do that with kind of getting the best of both worlds?
Finite field arithmetic, yes. You can basically do any arbitrary field you want because basically proving a modular equation modulo field is just going to be, show that A plus B is C plus whatever.
Oh, I see.
Witness times the modulus of the field.
Yeah, it's hard to go from only having finite field arithmetic to having integer arithmetic.
Yeah, but the other way is
reverse
significantly easier.
Yeah.
But proving operations over elliptic curves, I think encoding all those operations is going to be pretty hard. Right?
Yeah. Okay. Thanks.
What if you take the sync example? Then you don't need to even witness this quotient. You just prove that it's like all the equations are like
We don't hear.
Can you repeat?
right. So just to expand, like if you use the sync plus trick, right, then you don't need to witness all of these quotients when you go from integers to the field. You just prove that it lies in this ideal generated by whatever the modulus is. I didn't see the whole of the thing. Okay. Yeah.
Okay, a last question, very short one. Yes.
Okay, I found out the proving time, our proving time is incorrect. So we don't have a log B. We have MB polylambda log N. It's not even polylog. Just, okay, so thanks.
Okay, let's thank all the speakers for the session again.
Thank you so much for chairing these sessions. Everybody, just outside the hotel when you go out, we are now taking the group picture of all of us together. Please come join. It's immediately now. It's literally now.